So the next talk will be from Catarina Alves, who is going to tell us about optimizing supernovae classification. Hi, Catarina.
Hello, can you hear us?
I think I recorded a talk.
Yes. Okay, so we'll play your talk and we'll come back to you for question afterwards.
My name is Catarina, and I'm a fourth-year PhD student at University College London. I would like to thank the organizers for the opportunity to present our work. Today, I am going to talk about considerations for optimizing photometric classification of supernovae from the Rubin Observatory. First, I would like to thank my collaborators, Irania, Michelle, Jason, Tarek, and Raul. The motivation for this work is that the Rubin Observatory Legacy Survey of Space and Time, also short LSST, will discover at least an order of magnitude more supernova than the currently available. Traditionally, we would use spectroscopic sources to spectroscopically confirm the supernova. But with so many supernovae and limited resources, we must rely on photometric classification. Photometric classification performance depends on several aspects, in particular on the not-yet-finalized survey observing strategy. And this is the first study to analyze the impact of the LSST observing strategy on supernova classification. We use the dataset from the Photometric LSST Astronomical Time Series Classification Challenge, also short PLAsTiCC. It consists of simulated multi-band light curves for 3 years of LSST, simulated under realistic observing conditions, but a now outdated observing strategy. The dataset includes the different types of transients and variable stars. But in this work, we focus on supernova 1A, supernova 1BC, and supernova type 2. In the bottom of the slide, you can see examples of two light curves of this dataset. The PLAsTiCC dataset was divided into a simulated spectroscopically confirmed training set biased towards nearby brighter events. It is then a non-representative training set. And accurate photometric classification requires a representative training set. In this work, we built a classifier using the photometric transient classification library snmachine. Basically, we input the training set, augment it to deal with the lack of representativity issue, extract wavelet features, add the photometric redshift and its uncertainty, train a gradient boosting decision tree classifier, and we are ready to classify data. The original version of this library was previously used in sample papers. But in this work, we upgraded snmachine for use with LSST data. snmachine is now publicly available. For the augmentation, to deal with the lack of representativity, we augmented the simulated training set to be representative of the test set in terms of the photometric redshift distribution per supernova class, the cadence of observations, and the flux uncertainty distribution. This augmentation approach was based on Boom 2019, and it's basically generating new light curves from two-dimensional Gaussian processes. We can think about it as simulating the same supernova at different redshifts. In the right side of the slide, you can see the light curve of one of the original simulated events. And on the bottom, you can see the same event augmented to be at a different redshift. We also made sure that we have the same number of augmented events in each supernova class. Now that we dealt with the training set, we can now extract features. And we chose wavelet features because they are model independent and quite localized both in time and frequency. These are general features and can characterize many classes of transients. They have been shown to be successful for general transient classification, and this approach was also not previously used by any of the winning plastic entries. But exactly how do we extract the wavelet features? First, we look at our data, and it's not uniformly sampled in time. So, we fit the Gaussian process to interpolate between the observations. Then, we use this Gaussian process fit to estimate the value of the flux in each fast band in a uniform grid of times. Then, we use these now grid of fluxes and perform a wavelet decomposition. We now have the wavelet components, but this is a highly dimensional space that where only some of the components provide useful information for classification. Thus, we apply a principal component analysis and reduce the dimensionality to 40 components. We can always go back to the original real space and compare that we do obtain a similarly looking light curve, as we can see comparing the last image with the Gaussian process fit. Now, using these 40 wavelet features and adding the photometric redshift and its uncertainty, we have 42 features to train our classifier. In the training, we also use the weighted low-loss metric provided in PLAsTiCC. In the right-hand side, you can see the confusion matrix that we obtain. And you can see it as a strong diagonal, which means that we are able to accurately predict most of our events. This performance is comparable to the one obtained by the top 3 solutions to PLAsTiCC. But where are the implications for observing strategy? We study the classification performance for supernova with different properties within the single simulated observing strategy that is available in PLAsTiCC, and measure the performance using the recall, which measures the fraction of correctly classified supernova, and precision, which measures the fraction of supernova assigned to the considered class that are indeed from that class. One of the important properties of the observing strategy is the season length, that we can tune by taking additional observations in suboptimal conditions, such as high hair masses. And in this work, we use the light curve length as a proxy for the season length. We also focus on light curve lengths between 50 and 175 days, so between the two vertical black lines in the images, due to the small number of effects outside of this range. And we find that events observed for longer have better characterization by the feature extraction step and a higher recall precision. Another crucial factor of observing strategy is the cadence of observations, which impacts all transient science goals. And in this work, we use the internight gap to quantify the cadence. And we find that events whose median internight gaps is smaller than 3.5 times, so to the left of the black vertical line, are better sampled, have a higher light curve quality, and a higher recall precision. But an event can have these median internight gaps smaller than 3.5 days and still have a large gap. So, We also look at the effect of the number of large gaps with more than 10 days in events that already have a median internight gap smaller than 3.5 days. And we find that the Gaussian process fits can interpolate these large gaps if the median internight gap is smaller than 3.5 days. So in the figures, we see that the recall and precision are broadly independent of the number of large gaps. These results show that a median internight gap smaller than 3.5 days is sufficient for photometric classification. In conclusion, augmentation is crucial to obtain a representative training set. This is the first study of how observing strategy impacts the photometric classification. We find that longer light curves and events with median internight gap smaller than 3.5 days lead to a higher performance, but the number of large gaps have no impact. The results provide guidance for further refinement of the LSST observing strategy on the question of supernova photometric classification. And we also publicly release snmachine. In the future, we plan to investigate the dependence of classification performance on different observing strategy simulations. For each observing strategy, we simulate multi-band supernova light curves similar to the ones in PLAsTiCC and apply the methodology developed in this paper. Then we can quantify the difference in performance between the different observing strategies and produce observing strategy recommendations regarding the supernova photometric classification. Thank you for listening. I would be happy to take any questions now. Thank you.
Thank you so much, Catarina. We have time for a few questions. We have one in the audience. Are you back with us, Catarina?
Yes.
Awesome.
Hi, it's Niall Miller. Have you explored the effect of the number of photometric bands has on your accuracy? Like, because LSST has quite a few.
Yes, this dataset had 6 photometric bands, and I did not explore that in this work, but I am starting a new project with a different number of photometric pass bands. So stay tuned for more results.
Cool, thank you.
Another question? Otherwise, we have one on the Slack from Roberto Trota, who is asking if there is any influence of photo-Z uncertainties and particularly catastrophic photo-Z failures in your pipeline. So do you use the photo-Z information?
I use the photometric information, and in the training set is easy to avoid because we have the spectroscopic redshift. So for the augmentation, that plays no role when selecting the redshifts. But we want to make an augmented training set that is representative of the test set. So we do use the difference between the spectroscopic redshift and the photometric redshift to generate augmented events that also have that catastrophic errors to try to make it more representative. So we do take into account those.
Okay. Let's thank again Catarina.